In week number 2 of Geography 4010, Applied GIS, we cover coordinate systems. I think in this day and age with ArcGIS Pro and even its predecessor ArcMap, we took for granted the time and energy it takes into creating coordinate systems, declaring coordinate systems, ensuring they're correct, because they seem to superimpose on each other and not auto-project. And I'll talk about this in a second. Now, in this chapter, we're going to talk about coordinate systems and reference systems. We'll talk about map projections, limitations of map projections, and way to display nationwide and local data. In this day and age, when we're displaying data on a map, it's typically going to be on a phone or a tablet or a computer, or it's going to be displayed digitally instead of constant on a piece of paper or a PDF or TIFF or anything like that, which has a consistent scale. And so we've started to create a new projected or new coordinate system to display data that adheres to zooming in and zooming out instead of being consistent. Now, each projected or each data component, raster, vector, whatever else, has to have a defined datum, a defined coordinate system, and we'll talk about sometimes how they're conflated so they can be displayed with the same projection, so they can be overlaid and viewed together in ArcGIS Pro. And now you notice I did not say they need to be the same exact coordinate system. They just need to be defined so they can be overlaid with each other. And previously, when I got into GIS 25 years ago, all of your feature classes, and they didn't have feature classes back then, but coverages and shapefiles need to be the same exact projection so they could be displayed on the same map. We don't have that, but we have utilities to change projections. So when we look at feature data sets are containers within feature databases that need to have the same exact coordinate system. We can auto-project or project those, change the actual projection of those instead of auto-projecting them on the fly for the sake of the view. Now, the first issue we deal with is map scale. Map scale is based on the representative fraction, the ratio of distance on the map to real-world distance. And most GIS maps fall between about 1 to 1,000,000 and 1 to 1,000. Anything bigger than 1 to 1,000, 1 to 100, we're talking about survey grade, which gets out of the scope of GIS. GIS, we're scaleless because maps can be enlarged and reduced and plotted at many scales other than the original data. And so that's why they're starting to look at something called the Web Mercator projection system so that you can zoom out, zoom in, and zoom out of these with as minimal distortion as possible. We compare, we edge match or merge maps in GIS. They need to be at the same scale and have the same extent. And we'll talk about some of the challenges of those, especially when working with historic maps. And then we work with the metric system. It's much easier to use in GIS, but in North Carolina, we have the state plan projection system, which works in feet. And so when we kind of look at this, when we look at different scales of maps, we have the map of the United States might be like 1 to 100 million versus region, 1 to 37 million versus 1 to 16 million versus 1 to 1,000,000. And we'll talk about what those mean in a second there, 1 to what? Map distance versus real world distance. And so there's a lot of ways we can say this. We can have a numerical scale. We can have a verbal scale. So we can say 1 inch equals 4 miles because that's typically what I care about here. And so I look at something like this where it says 1 to 16 million. 1 inch on the map equals 16 million inches in real life. Now, how many inches is 16 million inches? And so we can divide that 16 million divided by 63,360, which is the number of inches in a mile, so we can get a better idea of that. And it's equal to approximately 250 miles. So we know that 1 inch equals 250 miles on this particular map. 1 inch equals 20 miles. And so every once in a while, you'll see maps at 1 to 63,360, depending upon what you want to map, so that 1 inch on the map equals 1 inch in, 1 inch in real life. Now, we're not going to make maps of the state of North Carolina at 1 to 63,360 because it would literally be 450 inches wide, which is the width of North Carolina. And so we need to have this reconciliation between scale, the area you want to map, how much paper you want to utilize, and everything like that. And so you can see a really good example of a verbal map right here. Because a lot of times when we edge match, we might be taking different parts of a map, and these are old traditional paper maps, and merging these together. Now when you look at a scale of like a baseball earth, their circumference is about 226 millimeters. The Earth's circumference is about 400 million meters. And so the scale is about 1 to 177 million. That's 177 with 6 zeros if we were to approximate the size of that. So typically we want our numerator to be a 1 because it could be 2 to 344 or whatever the math is, 344 million. But we don't want to do that. 1 inch equals what in real life? Because we typically see these when we start figuring out absolute location on a map, we use geographic coordinate system. Geographic coordinate system gives us angular distance, and you can see this from the NOAA website where we get latitude, longitude. I think this is some sort of type of temperature right here, but you can see this latitude's positive, longitude is negative, because these measure angular distance, and these are probably the most popular of measurements that we hear of on a regular basis. We say latitude, longitude right here. And you can see what these latitudes and longitudes represent. These represent angular distances from the center of the Earth. Now, latitude actually measures up and down, north and south. Even though we say latitude, longitude, latitude really represents the y, the y factor, while longitude represents the left and right. Now, this left and right is from the prime meridian, which is the reference point. For north and south, it's from the equator, the line that separates or cuts the Earth in half between the North Pole and the South Pole. It's a little more difficult with the prime meridian, which was kind of created, formalized about 150 years ago, 140 years ago, as to be kind of the zero reference point for longitude. But just remember, we say longitude, it really goes longitude, latitude. We say latitude, longitude, but longitude represents the x, latitude represents the y. And these are angular distances. So imagine trying to convert these angular distances to real world distances. We've got to deal with the sines and the cosines and the tangents and all that other stuff that we probably most of us want to forget from math class. So the geographic coordinate system of the Earth's latitude and longitude system, ranging from 90 degrees south, negative 90, to 90 degrees north in latitude, and then 180 west to 180 east in longitude. And we know for a circle there's 360 degrees in a circle, so it covers the entire circle and the entire globe. So a line with constant latitude running east and west, that's called a parallel because they don't meet. And then a line with constant longitude is what we call a meridian. And the 0 degrees one is called the prime meridian. And then on the other side, it kind of coincides with what we call the international date line. So the 0 longitude meridian is called the prime meridian, and it passes through Greenwich, England. Sometimes you might see the term GMT, Greenwich Mean Time. That's the time it is in England right there with our time zones and everything else. But when we put the parallel of grids and meridians together, it's what we call the gradicle. This is an example of a gradicle. There's tons of different gradicles out there depending upon your projection here. And so you can see here over in the United States, we have negative longitude, positive latitude. So if you think of it as quadrants, it's kind of like your first quadrant, second quadrant, third quadrant, fourth quadrant from math class. This is like our second quadrant right there. So we will see some negatives right there. Now sometimes we call it west longitude instead of negative, but I did show a perfect example right there from our NOAA data where it gives us longitude as a negative number. And so we can see examples right here, as we can see examples here of our gradicle here. This is a slightly different gradicle where these lines aren't necessarily straight, and that's because of the projection that we have. And then we can zoom in even more and more, and you can see, the local city here with much less distortion. But this is a picture of the prime meridian. It's in Greenwich, England right here. So it separates your eastern hemisphere from your western hemisphere, or that the equator is a little bit more distinct. Separates the north from the south. There's really no debate on it there. And this was just taken from the International Meridian Conference in Washington, D.C. of 1884, where they're starting to standardize, time and time zones and so that, travel, especially with travel, could be standardized. Now, the shape of the Earth, it's not quite a sphere, okay? And so it's what we call an ellipsoid or a spheroid. And so this sphere is about 40 million meters in circumference, distance around it, which is about 24,000 miles, a little more than 24,000 miles. But it's a little bit thicker, okay? The circumference is a little bit higher at the equator as opposed to the distance around one of these meridians. And it's only about 1/297th off. But when the Earth spins, it's got a little bit of a bulge. Okay, because the Earth is not truly a solid, it's kind of a semi-solid, We have the inner core and the outer core and the asthenosphere. And so we have these ellipsoids that we use to try to find absolute location. Now, when we look at an ellipsoid, this is the actual mathematical equation for an ellipsoid here. Now, this isn't perfectly Earth because we have undulations and all those other things there, but this is what we're looking at here. We have the semi-major axis, we have the semi-minor axis right here, which is a little bit less right here, but for WGS 84, you can see this number is about 1/298. We sometimes call it the flattening ratio right here, and these numbers are always changing. You can see these numbers because we've never measured to the sun of the Earth right here, 6,378,137 meters. And so we've never measured that far. And so with increases in technology, these numbers are changing slightly, and this number is changing slightly as well. And so we've got new datums and new ellipsoids that will be creating on a regular basis. Is that going to impact our everyday lives? Probably not. But just keep note of these flattening ratios might be slightly different and have really evolved since we started creating large-scale models of the Earth in the 1860s. Now, we can view projection information by going to the map and clicking on coordinate systems and show us all this. I'll talk a little bit about this projection information, but this is all the nasty math stuff that goes on so that these data can be superimposed on a map with other projections, and the computer understands it. There's probably thousands of different projections. We use these for different purposes and whatnot. And so we have these different projections right here for this map. So the actual map, which is composed of multiple layers, might have the same projection. And so we have things like standard parallels. This is called the North Carolina State Plane Projection, so it's used to minimize the distortion for the state of North Carolina. So if we were to display it for some other state, we're probably going to have some type of distortion. We'll talk about what those distortions are. But you can see the geographic reference system, how far a degree actually is, the semi-major, semi-minor axis right here, and the inverse flattening or our flattening ratio. How we model the Earth, we've got the sphere, we've got the ellipsoid, we've got a geoid, and now we have topography and heights on top of these. And so when we actually start looking at the field of geodesy, which is the size and shape, study of the size and shape of the Earth, we can really go down some rabbit holes with these, and I'm kind of giving you the quick version of these. A datum is the mathematical algorithm used to create the 2D map from the three-dimensional spheroid. So we've got a couple different datums out there, and I alluded to the NAD 83. There's something called the NAD 27, and they're about 200 meters off. I previously worked for the military, so when I worked for the military, we would get data that's unprojected, and we'd have to figure out, declare a projection for it. It just had no projection information. And if I have time at the end of this lecture, I'll show you what data with no projection looks like. We've got to give it a projection information. And so we give it projection information, and we saw that, hey, let's compare it to a DRG. This is called a digital raster graphic. And if our data looked like this, it was probably off. We were probably using the wrong datum. Because when we look at the equatorial distance for NAD 27, 6378.206 kilometers versus the equatorial radius for NAD 83, 6378.137, it's about a couple hundred feet off, a couple hundred feet different. Which one's right? No, this NAD 83 is probably a little bit better because of advances in technology, but this was the equatorial radius from a lot of the data that were created in the first half of the century and even good parts of the second half of the century. So it's important we understand those. So when we look back here, this geographic coordinate system is NAD 83. So if we were to change this, our data would be slightly off. And you would notice, and we notice this because it doesn't line up. Most of the data that we work with, the data lines up ready to go. But you can see for NAD 27, you can see I've got this NAD 27, and you can see these numbers are slightly different right here. A much different flattening ratio as well. These numbers are just slightly different right here. So we have map projections. So we have these ellipsoids and geoids, but a map projection is a transformation from the 3D to a 2D. We do this all the time when we wrap up Christmas presents or birthday presents. That flat surface, the wrapping paper, is our 2D, our present is our 3D, and the one thing we know, whenever we wrap up a birthday present, a Christmas present, we're always going to have a little leftover paper. Now, what do we do with that paper? We just kind of fold it over a little bit and go about our lives, but how do we deal with that mathematically and cartographically? So a projection is the method by which we put this 3D onto a 2D and try to minimize distortion as much as possible. We'll talk about some of these different types of distortion. A projection puts on a flat surface, such as a cylinder or a cone, but projections that preserve the shape of features are called conformal. Projections that preserve the area of features across a map are called equal area or equivalent. And this is kind of what you think of it. We've got a 3D and we put it onto a 2D. And as you can imagine, the larger areas, if we need to map much larger areas, there's going to be a lot more distortion than if I map a smaller area. And so we have what we call azimuthal projections, cylindrical projections, conic projections right here. And if you saw before, when I have that map of North Carolina, the top edge of North Carolina was curved a little bit. You notice right here in the bottom right, the top edge of the United States is slightly curved. Is it curved in real life? Hopefully everyone's saying no, but it's not curved in real life. Why is it curved here? Because that projection is not going to mean, the east-west is not going to be maintained. East and west really isn't left and right. It's along this curve right here. So right along this curve right here, that's east and west. So I alluded to the idea of we're always going to have some type of distortion. It could be shape, area, direction, or distance. This is what we call the SAD principle. So whenever we put a 3D onto a 2D, we're always going to have some type of distortion. So no flat map can be both equal area and conformal. We're always going to have some types of trade-offs. And so I've got a kind of a list here of the different types of projections and what they preserve. And like I said before, the larger areas that we have, the more disrupted, the more distorted it's going to be in some way, shape, and form. And so we have different map families here. I don't want to focus too much on these. I want to focus more on the practical. But we have different map families like Albers equal area. That's a big, I'm a big fan of that. When we project it onto a cone and then we lay out that cone onto a flat surface. And so For the state of North Carolina, we looked at the idea of standard parallels, which are focused within the state of North Carolina. So this is for the United States. We have standard parallels where distortion is minimized, and then we have distortion throughout here. And these are basically mathematical algorithms that are able to apply this. And so we can look at this distortion here. So for the entire United States, or this is for the state of North Carolina, you can see standard parallels, our latitude of origin, which is pretty much halfway in between, and our central meridian, which is somewhere in the middle of the state. So we're really focused on the middle of the state so that we minimize distortion for North Carolina. This example here is for the entire United States, but this is for North Carolina. This is for the entire United States. So you can see standard parallel 1 is negative 29.9, 45.5, negative 29.9 is just 29.5 is just south of New Orleans. And you can see that parallel right there. And then the central meridian is negative 96, which is in the middle of the United States. And so you can see that the geographic coordinate system is based on NAD 27, but your computer does a lot of this for us. But you can see these different standard parallels for what we're trying to minimize distortion for. This is another one. It's called the azimuthal. These azimuthal projections are typically used in our polar regions. Our polar regions get a little weird or different up there because you go further and further north. These meridians converge at the pole where that our parallels never intersect with each other. So we have kind of really gross and great distortion with our distances here. So we have polar stereographic projections right here. And so the one good thing about these is that it represents the great circle as a straight line. Great circle is the shortest distance between 2 points on a globe. We know that a straight line is the shortest distance between 2 points on a plane. We can calculate the distance between those. But when we see these type of azimuthal projections, it's approximated as a line here. Approximated as a straight line, because when you fly from, let's say, Los Angeles to Japan, you actually kind of fly over, Alaska and Russia, North Korea, and you need to be aware of the volcanoes here. So when we actually look at it, it kind of takes this route right here. Takes this route. If you can follow my mouse right here, it doesn't fly this way because that's not the shortest distance on the globe. Okay, it's not the shortest distance on the globe. Other types of map projections we have are what we call cylindrical projections, meaning it approximates the Earth to be a cylinder. We know in reality the Earth is not a cylinder, it's a globe, but flattening that, especially at the polar regions, gets increasingly problematic. So different types of projection families include Mercator, UTM, Universal Transverse Mercator, and what we call cylindrical equal area. This is a projection called the Mercator projection, and we need to be careful about this here. Now, there are some good things about this. Up is north, down is south, left is west, right is east. We see these lines of latitudes and longitudes, our parallels meet at right angles, which we look at the North Carolina State Plane projection, they don't. But as we get further and further north, we know that there's going to be what we call aerial distortion. So we see this thing here called Greenland. It's about 840,000 square miles. It looks to be about the same size as Africa or South America, but it's really in reality much, much smaller. And so we have aerial distortion here because in theory, as we go further and further north, these lines of latitude are going to get smaller and smaller and smaller until they converge to a point at the pole, in this case, the North Pole. So there's advantages and disadvantages of each of these projections here. So I just wanted to kind of show a couple of these as well. We have coordinate systems. It's a standardized method for assigning codes to locations so that we can find absolute location. Our standard coordinate system uses absolute location. And typically when you type in your address to a phone, all it does is turns that relative location into an absolute location. So the map is captured in units of paper based on relative location. it could be meters, it could be feet. We have X direction, was what we call eastings. Y values are called northings. And so a lot of times with our coordinate systems, especially for the one in North Carolina, which I'm focused on, we try to make both of these values positive because we don't really care about Texas when we're displaying information using the North Carolina state plane projection. We'll change it to the Texas state plane projection. So we have different coordinate systems for the U.S. We have some focused on states, focused on continental U.S. We have them focused on particular continents. We have military grid reference systems, state planes, UTMs for larger areas. And then we have geographic coordinates, which flatten these out. And then we have something called Web Mercator as well, which is focused on how do we display data that we can zoom in and zoom out on. So a real quick look at a couple of these is UTM has different zones. When I worked with the military, each zone was 6 degrees wide. So we have 360 degrees in a circle. So there's 60 of these zones. And they were just measured eastward. And so as we said, zone 17, we have an easting and then we have a northing from the equator. These are some of the UTM zones that we have in the United States. So if you're working with like nationwide data, you might be working with UTM, and then that's based on something called MGRS, Military Grid Reference System here, which is based off of UTM. So we can find absolute location for zone 14 at this particular location right there. And this is going to be distance east of this line of longitude and then north of the equator. Now we can use GCS to portray maps. We can convert, and so these are some of the projection and transformation tools that we have. We can define a projection. So once in a while you might get data where you don't have a projection, so that you can define the projection, you can reproject it here. So these are really powerful tools. We'll show an example here, I hope, because what we're going to do in this exercise is we're going to download some neat maps from the North Carolina Digital Library and bring it into GIS, and then you're going to have to give it coordinates based on coordinates that we already know. And so you can see what some of these different projections look like. This is the North Carolina state plane projection. You can see the top edge of North Carolina is curved slightly. We know that it's not in real life, but this is what it looks like as GCS. The same exact map using one or the other. I like North Carolina state plane for North Carolina because to me this looks a little bit kind of stretched out. These are buffers using North Carolina state plane versus GCS, Geographic Coordinate System. We also have Web Mercator, and this is kind of the direction people are going because these days we're going to share our maps to services, and we'll look at these on screens and tablets and whatever else. We'll zoom in and zoom out on these instead of creating kind of dedicated projections for these. So this is the de facto standard for web maps and online services. It's defined on WGS if they were defined on a sphere, but it's a conformal, so it tries to keep directions, angles maintained at an infinitesimal scale, so when you zoom in or zoom out. And this has been really, to me, it's been really creative. The one issue that we talked about with Web Mercator, just like Mercator, is that we have aerial distortion, especially towards the polar regions. But this is an example of kind of what we look at here for Web Mercator, because with these maps, you can zoom in, you can zoom out, you can do whatever you want to do. Another thing that we do have, and we have information about projection, it's also going to be stored in the metadata. So it tells us a lot of information about the metadata. So the projection information that's been collected for these as well. Now we also have state plane coordinate systems. State planes were created to provide local reference systems that are tied to the national datum, like NAD 27, NAD 83. But the whole goal of, say, North Carolina state plane projection is to minimize distortion for the state of North Carolina. New Jersey projection system is to minimize distortion for the state of New Jersey. Okay, nothing more, nothing less. And so I wanted to go down a couple of rabbit holes here, but we have the North Carolina Geodetic Survey. It keeps survey markers which mark the exact latitude and longitude of places within the state. Here I'm at Swinging Bridge here out at not Hanging Rock, Grandfather. I think it's Grandfather Mountain. Yeah, Grandfather Mountain out in out past Boone. And you can see it's got this North Carolina Geodetic Survey here, placed here in 1970, which helps give us our exact latitude and longitudes, so that they can be part of this network. So that ties in with GPS, satellite phones, all the other features that we take for granted. Here's a survey marker here, and this is a USGS survey marker, but this is right on Fayetteville Street as you walk across the street. So there's one of these, and there's another one of these down near the Lee Biology Building. I thought this one was interesting. This is a survey marker at my wife's late grandmother's house. And so it's got a survey marker, and then you actually look in, and then there is the top of the survey marker. So I always thought this was kind of neat right there. But when we look at this for the NGS data sheet here for Swinging, it's in Avery County, it's at Grandfather Mountain, you can see all this kind of math information that gives us, that tells us what's going on here. Okay, about this particular feature. So there's a lot of math that you can get into. We have conversions with feet, we have conversions with meters. It's really interesting. Last thing I will talk about here is that data creation using the internet or other sources. So every once in a while we might get data where we can download imagery or whatnot from these, and we have an X, a Y, we have a northing and an easting. Just make sure you know which one you're using here, because states like Kentucky have a north and a south zone, where that North Carolina just has a single zone. So I really implore everyone to be careful, because you can see some of these zones that we have, and they kind of break these zones into conic projections like North Carolina, Tennessee, or cylindrical projections that we have for like Idaho and Wyoming and Nevada here. So last couple things I will mention right here. This is what we look at here when we look at exercise number 2. And if I were to right mouse click and look at properties, I know I've provided some tutorials here. These are coordinate systems. These are different coordinate systems here. You can see I've got some favorites right here, but this is the Web Mercator. If I were to change it to Web Mercator, this is how it looks like in the Web Mercator. Because the Web Mercator, you're zooming in, you're zooming out, you're doing a lot of different things here, as opposed to just one of them right here. This is the NAD 87, this is the NAD 83 state plane, but this is for North Carolina. And I can start to zoom out and look at the tilt right here. Look what it looks like in Africa or Asia, because it really doesn't care about what any other state looks like. And I can do the same thing here, where I go to Properties, and I can go and pick out some of my other state planes. Now look at how they're divided here. I've got my different layers here, but I've got different geographic coordinate systems, which measure it using latitude and longitude, or I can look at projected coordinate systems. So I have different continental systems, state planes, solar systems, a lot of different, projected systems here. So state plane, these are the different units that we have here, and typically I just like going, NAD 83, US feet. This is typically only a problem here when I create feature data sets, but I want to display it for, say, Minnesota Central. What does North Carolina look like for Minnesota Central? Looks like this. Why? Because if I were to zoom into Minnesota, I bet you Minnesota Central is going to be nice and even, or whatever the right word is, non-tilted, but it doesn't really care about the rest of the rest of the United States, because we've got a North Carolina state plane projection that does that. Now, last thing I'm going to talk about here, because and I provided a tutorial on it, is that we have a really neat resource here related to maps. And I can go to, say, Durham County right here, and this is the web library at North Carolina Maps, but I can go to, say, Durham County Maps, And I can look at different maps of Durham. These are paper maps from 1881. And I can look at this paper map right here. I can download Chatham County, Alamance County, Orange County. So I can go and download these things and then superimpose these on a map. Now I'm going to download this thing right here because I'm going to show you some of the challenges that we work with. Because as you can imagine, no one ever really thought of GIS. And I'll download this as a large as well, just in case. There we go. Okay. So we got a map of Durham County, because the one thing I do want to do is I kind of want to look at this in a GIS. That'd be really neat. Really neat to bring this into a GIS, because I see I have some reference points here. I have Alamance and Chatham County, Caswell County, Person County right here. So I've got some reference points here. So if I know where these points are, I can superimpose it on top here and then add these. Okay, and superimpose it on my map. And there's a whole rich kind of body of knowledge related to historic maps, putting these on top of each other. Here I'm displaying these as feet right here. So you can see I've kind of displayed these as feet right here. So now you can see my state plane coordinate system. And I go down here to somewhere in Alabama, and there's somewhere down here, there's a 0 point right here near Alabama. So that everything for North Carolina is in the first quadrant, meaning they're always going to be positive right here. Will always be positive. But I can go and add data to this. I can definitely go and add data to this. So I can go to my features here. So I'll get the name of it here. The name is map. Here it is. Well, let's display it. There we go. We're going to add it there. All right. You see what it says here? Map is missing coordinate information system. Click here to view details. So those are some of the challenges you run into, because when we measure, this is just measured in pixels. So if I were to right mouse click and click on zoom to layer, you're going to see where this thing's sitting right here. It's sitting, it should be sitting right down here somewhere in Alabama at the 0 coordinates here. Now, at this 0 point right here, which is the basis here. So what our goal here is to do is to somehow give this coordinates here. And I've got tutorials on how to do this, but I hope I covered projection systems as well, and some of the challenges working with these, because I think those of you looking for neat research topics which blend the quantitative and qualitative, these historic maps, and bringing information like this, into GISs and superimposing them with each other. There's some really neat projects here related to, phenomena, soil maps from 1920s. We've got red lines right here, which is really pertinent even in this day and age. Building zones and things like that from the 20s and 30s, long before digital GIS. I think there's great, opportunity here. And these are some of the work that we've done here. You can see some of the literal, redlining that's done here in, the city of Durham right here, that there's just so much research possible related to that.